talk on coded matrix computation. This is joint work with my two former students, actually, Lee Tang, who works for Pinterest, and Anindya Bijoy Das, who's a postdoc at Purdue right now. So this talk is about what would you do if you wanted to do large-scale matrix computations in the cloud. So here we have some names of some of the vendors that we're all familiar with. And basically, I think at least in my group, a lot of the large-scale computation we do nowadays is on AWS or other related code platforms. So they are being used. And I guess some years ago in the information theory community, we had this realization, I guess, that coding techniques could also be used for protecting against speed variations, which are somewhat endemic in cloud computing, and also failures. Okay, so we have some. I said failures and it happened. Okay, let me try one more time. All right. Okay, it's not. So I'll just use. Yeah. He put. Yes, it is there. Sorry. Or could I just? I could just use this as well. Okay. Yeah, I'll just use this. Yeah, that's fine. Oh, wait, sorry. Even this is not working. Oh, okay. Now it is working. Yes, thank you. So I guess the overarching question here is how can coding techniques address these issues within distributed computation? So I guess the prototypical problem that we are going to be considering here is, actually the only problem that we are going to be considering here is matrix computations. So by which I mean matrix vector multiplication or matrix multiplication. So let me motivate the problem here by the matrix vector case. So you have this big matrix A and a corresponding vector X, and you're trying to compute this matrix vector product. And the scenario we're in is that this matrix is too big to just schedule it on one node. So I guess the naive way to do it would be to simply, just chop this into 3 block rows and give it to 3 different nodes. But the problem with that is, of course, that if one of the nodes is slow or is failed, you are basically dominated by the speed of that. So what can you do for this? This is, I guess, perhaps the first paper in the area of coded computation going back to 2018, at least that I am aware of. So the idea is nice. So what you do is you now chop your matrix into 2 parts, but now you, let's say have a systematic part where nodes 0 and 1 are computing the systematic matrix vector products, but then your second, your W2 is now computing a so-called parity matrix vector product. And it's clear that if you get any 2, then you can actually decode the result. Okay. And this has a nice generalization to the case of matrix multiplication. And this is work due to Salman Avastimer's group. So once again, you chop your 2 matrices into smaller parts so that what you are giving to workers is now going to be a smaller submatrix. So essentially, each worker is going to compute less. But now you do it a little more carefully, meaning that you encode the matrix A and you also encode the matrix B. And so each of these workers is operating now on encoded matrix products. So they're completely oblivious to what encoding is going on, though. And basically, you can see that whatever a particular node calculates can be thought of as evaluating this so-called matrix polynomial at a particular point. And so if you have enough evaluations, you will be able to decode. Okay. So that is I guess, the first few ideas within coded computation. So essential idea, if you were to summarize, would be that you would embed the computation into the structure of a Reed-Solomon code. And it's going to be basically resilient to the maximum number of node failures, and that follows from the number of nodes that you need to, number of evaluations that you need to get for interpolating the result. All right. And so in this domain, the so-called recovery threshold is the minimum number of nodes that need to complete their computation so that the master node can decode what it wants. Okay, so far so good. So here is one thing I would like to point out. So this is what the structure of equations looks like when you're trying to decode. So you would be getting some square submatrix of this. So maybe let's say the top 4 by 4 system of this. And this is basically a van der Waals matrix, right? So now what is the problem with this? Now, if you want to think about van der Waals matrices over finite fields, there's no problem. The only thing we care about is decoding. Whether the matrix is invertible or it is not invertible. And that's why basically Reed-Solomon codes work in some sense as very good erasure codes or MDS erasure codes. Problem is when you start doing this over the real numbers, there are issues. And the first major issue is that van der Waals matrices have very bad condition numbers. So my definition of a condition number is going to be the ratio of the maximum to the minimum singular value of the matrix, all right? And so in numerical analysis, a general thumb rule is that if you're trying to solve AX equal to B, condition number of 10 to the power of L leads to approximately these many bits, L bits of loss of numerical precision. So you don't want your systems of equations to have bad condition numbers. It just doesn't work. So here is an example. So this is, this is a simulation from MATLAB. So you have a degree 9 polynomial that we are trying to, let's say, recover from noisy observations. And just all I did was, you add it and you add a little bit of noise to it and try to see whether you can recover. So this blue curve is where the evaluation points are so-called integers. This red curve is so-called where your evaluation points are sampled uniformly from -1 to 1, in that range. The position, these are the points where you're actually evaluating your polynomial. So you see that even for such a small degree polynomial, you have a significant amount of error. Okay, and so you can anticipate that as the degree of the polynomial becomes larger, even a little bit of numerical inaccuracy can really blow up. Okay, so the first part of our work, that is the first motivation, so we identified this problem within coded computation, or at least the then methods of that were widely prevalent for coded computation. So the second motivation comes basically from what I would call partial computations. So if you think about trying to use an MDS code in this scenario, what you're really saying is either a node is working or it's not working, right? So you are basically saying if a node is slow, let's think of it as an erasure. But that's not what is the real scenario in practice. So if you look at AWS, especially if you try to allocate some of those cheaper T2 micro machines, many of them are slow, but not necessarily failed. So the question is, so can we try to somehow leverage what the partial computation that is being performed by these nodes? So here is an example. So again, so going back to our basic example, so here, 3 nodes, you're trying to calculate, I don't know how well you can see this, but you want to calculate these 3 submatrix vector products, all right? So out here, you can see that suppose one node is failed, one node is, let's say, slow. So in other words, this is operating at roughly half the speed. Upon inspection, you can verify that as long as you get 3 submatrix vector products across all the cluster, you can still decode. So in this case, Q would be 3, which actually matches the minimum number that you need to find. This is another example where, let's say, I guess maybe it's not so easily seen here, but suppose that this node is the fastest, this node is second in speed, and this node is third in speed. You will still need to get 4 submatrix vector products in the worst case before you can actually decode, whereas you actually needed 3 at the bare minimum. Okay, so the goal, therefore, would be to try to maybe sub-packetize your job. Yes?
Why can't you break each worker to 2 and give 1 slice each and use the standard code?
So, I mean, the assumption here is that you have access to 3 workers. So you are considering a scenario where there are 6 workers then? I mean, no, you could, but I'm saying that
protection.
No, so I'm saying, okay, so let's say you're given a certain number of workers. So then what can you do is the question.
I guess one worker could act as 2 workers.
Excuse me?
One worker could act as 2 workers.
Right. So, but then, I mean, assuming that, okay, so I'm assuming that every worker here has one CPU is operating sequentially. So every worker has some notion of I'll do this job first and this job second. If it's a multi-core CPU, you can think of it as 4 CPUs, and then still every CPU is going to operate sequentially within itself.
The middle one is slow. He could send, he will be done with at least one of the jobs.
Right. So that's the idea. So, for example, out here, this one is working faster, and then this one is working slower. But I'm assuming at least when I'm scheduling, I don't know in advance who's going to be fast or slow. So I'm going to allocate the same amount of jobs to all the workers.
Right, but if each of them has several slices and doesn't...
Exactly. So that's exactly what I'm coming to. So the idea is exactly what you're saying. So you sub-packetize your job more. So you don't operate at the, you chop your job into finer parts and then see what you can do.
I think why is I understand the left side. Any three is going to work. I'm a little. Why is q equal 4 on the right side?
So it's possible, for example, that imagine that this one is kind of very slow. So while this one has completed these two tasks, you're still waiting on the copy of A0, so to say.
There's no coding on the example on the right.
There's no coding on the example on the right. It's simply replication.
There is a way to get 3 that doesn't work.
We are trying to say what can happen, when can you decode even in the worst possible case. So that's what I mean by this Q by dirt. Yes.
Does this require a longer block length? Because you're going to send a bunch out that might not get returned to you.
Mm-hmm.
So you have to have, you don't want to evaluate at the same point twice.
So yes, there's really no notion of block length here. It's just a notion of how finely you want to split your job. So the assumption is that the matrix is really big.
There might be a number, I guess. Since that continues out, there might be a number of points, right? If you're like picking integers, there's only so many integers before you evaluate at the same point.
No, because there's no that's going to be this. You can evaluate.
Yes.
But if you don't actually have an infinite number,
Well, that's pretty
and
hard.
obviously you don't want to evaluate point with 2 points too close together. That's not good.
So yeah, so that would be an issue if you are only restricting yourself to the class of, let's say, polynomial schemes, right? But as I said, polynomial schemes have their own issues. Any other questions? Okay, so the last motivation is the case of sparse input matrices. So a lot of the actual use cases where you're doing large-scale matrix computation, your matrices A and B are actually not dense. In many cases, they're actually sparse. And so I'd like to point out that if you try to use like an MDS code approach in this case, there are going to be issues. So let's do this. So suppose that these matrices are, the original matrix is actually quite sparse. Now, if you split it into 3 parts and you try to make this linear combination here, imagine that, let's say, only 2% entries randomly chosen are non-zero, just as an example. When you are going to combine 3 of them, the number of non-zero entries here will actually go up to approximately 6%. Basic probability calculation, not exact, but approximately. So basically what is going on is this. So if suppose you took alpha amount of time to calculate A transpose X, A0 transpose X, which would be the case when you're not doing any coding, will take you approximately alpha over 3, or should take you alpha over 3. And when you're doing this distributed computation, you want to leverage the time advantage that you're getting. But if you do your coding in this way, you're back to square one actually, because each individual node, what it is calculating, will take you almost as much as the original one will. Okay, so you lose the time advantage of this. And this, by the way, is an issue. It's a serious issue because, like I said, a lot of the large-scale computations are actually done on sparse matrices. So you want to not code too much, let's say. Encoding weight, you want to keep it as low as possible. Okay, so all right, so this is the fundamental problem. So let's say again, polynomial code fails to preserve the sparsity of these input matrices, and so the worker computation time is going to go up unacceptably. Okay, so in the remainder of the talk, and I think I've already taken quite a bit of time. I have some time. Okay, great. So let me talk about what we've done for numerical stability now. All right. So we've done some related work. We had some work on convolutional coding-based approaches and some work with Pascal One-Table based on universally decodable codes. And then, of course, Vivek Kadambe's group had this work where they tried to use, again, polynomial-based approaches, but worked within a different basis. And this basis is called the basis of orthogonal polynomials. And they showed basically that if you think about decoding, and whatever I'm talking about is actually for matrix multiplication. They said that if S is the number of stragglers, the worst case condition number of these decoding matrices will grow at most as order n to the power of 2s. All right. And then Krishna's group here, I mean, they've done a lot of work in this topic, and they've used random linear codes. So these codes are basically setting the encoding matrices as random linear combinations of submatrices of A and submatrices of B. And I will compare with these works in our results as well. Okay, so this I already talked about. So there is a very interesting paper by Victor Pan, and this paper is titled "How Bad Are Van der Waals Matrices?" All right, so let's say that this is an M by M Van der Waals matrix, and this one is these are the parameters S0 through Sm minus 1. So the work of Pan. So here is what, if I were to summarize the results of Pan, are what they show. So they show that if your parameters are real, then the condition number is going to be exponential in M. There's basically nothing you can do. Now, if you have complex Van der Waals matrices with parameters not on the unit circle, so imagine that you're choosing them at complex locations, but they're not on the unit circle, then the condition number is still quite bad. The statement is somewhat technical, and it's not as bad as the real Van der Waals case, but it's quite bad. All right, and so essentially one takeaway from this is if you are working with Van der Waals matrices, the only time you have good conditioning is if all parameters are on the unit circle. Right, so all your points have to be on the unit circle. So then a natural question is, suppose, again, going back to this matrix vector multiplication example, can I choose my evaluation points to be, let's say, complex numbers, or just on the unit circle? And the problem with this is that, let's say, if you're multiplying two complex numbers, it's going to be 4 times as expensive as multiplying two real numbers. So if possible, you don't want to take this hit in computation time, right? So what do you do in this scenario, right? So if let's say the problem that we are confronted with is we are trying to leverage the conditioning of Van der Waals matrices on the unit circle, but we don't want to actually do the complex computation. So if I were to summarize this entire numerical stability aspect, what we have is that we can do coded matrix computation with real values. Everything is real, and there is no bump in computation time, but we obtain the conditioning of Van der Waals matrices that have unit circle parameters. All right. So, and informally, what we have is for both matrix vector and matrix multiplication problems, our scheme has the so-called optimal threshold tau, which is the optimal threshold that was derived in the work of Salman and co-authors. And the worst case condition number is upper bounded by this quantity. So think of n minus tau as the number of stragglers that we're trying to protect against. So it's n to the power of s plus some constant. So, I mean, the standard way, I mean, if you take the a plus ib representation, I think you would have to do 4. Represent it in polar. So then you'll at least the twice, right? Also the phase.
But addition, you have anyway many more additions. If you convert the problem, not a conversion cost.
I don't know. I mean, in general, if you try complex multiplication.
There's one that did it in 3, though.
Yes. So there is a Strassen type algorithm, if you can do it in 3.
It's always like if addition is actually a problem, then at some point you have anyway the problem, right? So I think addition, it doesn't cost anything. It's really fun.
No, but here's the problem, Rudiger, because let's say if you do an intermediate step and you're adding a bunch of complex numbers, you will have to convert that also into polar form. And that is a non-trivial cost. Thank you. It took me time to think about that. Okay. All right. So let's think about why this works. So why are Van der Waals matrices on the unit circle good for us? So if you think about the classic DFT matrix that we all are extremely familiar with, this guy has condition number 1. So as perfect as it can be, right? But the problem is, of course, that when you are doing coded matrix computation, you don't get the DFT matrix, right? So you're going to have like a big matrix and you're going to get some submatrix of it. Okay, so here is one of our main results. We say that if I have an m by m Van der Waals matrix where these parameters of the Van der Waals matrix is chosen as a subset of the qth roots of unity, so then the condition number of that matrix is upper bounded by this quantity, right? So this is our, and this upper bound, as long as the number of stragglers, so think about q minus m as being the stragglers that you are trying to protect against. If this number is small, this is going to be a constant. All right, so what are the sketch of the ideas? So we are going to be using, informally, what we are going to be using is the properties of rotation matrices and circle and permutation matrices. So instead of evaluating at unit circle point, I'm going to, roughly speaking, I'm going to evaluate at this rotation matrix. Now, what is the property of this rotation matrix is that, so it has, okay, so it has eigenvalues e to the j theta and e to the negative j theta, okay? So, and likewise, if I look at a L by L circle and permutation matrix, it also has eigenvalues that lie on the unit circle. Okay. So if I were to, with some abuse of notation, what I'm doing is instead of chopping my matrix into A0 through AK, let's say, I further chop it into another part here. And instead of placing a complex evaluation point here, I place a rotation matrix here. All right. So what would this look like if, let's say, in the case of 3 workers? So the first worker would be assigned these 2 jobs in this order. Second worker would be assigned these 2 jobs, and third worker would be assigned these 2 jobs. So this would be the rotation matrix at theta. This would be the rotation matrix at 2 theta. All right. And so let's see why this works. So if workers 1 and 2 finish their work, then decoding is going to amount to decoding with this matrix, solving a system of linear equations with this matrix. But so essentially what I'm looking at is what is the condition number of this matrix. And that you can easily look at by doing an eigenvalue decomposition. So you can find a unitary matrix Q here such that, when you do its decomposition, it's going to look like this diagonal. And these 2 are now going to be points on the unit circle. So so if you think about the general case, right, when you're recovering 2, then it is going to look something of this form, okay, which can be rearranged to be put in the form of a block Van der Waals matrix. So you have a Van der Waals matrix here, a Van der Waals matrix here, but now the parameters are on the unit circle. Okay, so you can do something similar with circle and permutations. So again, think about, we are evaluating it on the circle and permutation rather than the complex point. But this requires a little more ideas. You have to create some so-called pre-coded matrices, but this gives you the advantage of fast decoding using, FFT and IFFT. So I tried to build the intuition with matrix vector multiplication, but all of this extends with some somewhat more messy algebra with for matrix multiplication as well. So except that now your encoding matrix for GA, which is how you're encoding your A matrix, is going to look like, once again, it's going to look like a Van der Waals form, except that you're placing rotation matrices. Likewise for B. And suppose that a certain number of workers return their results. The relevant submatrix that we are looking at is going to look like a set of column vectors where each of these are going to be the corresponding the tensor product of the corresponding columns, so the so-called Khatri-Rao product. And so if you do a little bit more algebra with Khatri-Rao products and Kronecker products, you can actually make the whole thing work, and you can recover that theorem that I talked about earlier, where we get that upper bound on the condition number. All right, so here are some numerical experiments. So if you have 31 workers with storage fractions 1/4 and 1/7, then the original work of Salman and co-authors tells us that the threshold is 28, all right? And so if you use the polynomial codes, which is their approach, the worst case condition number, this is log to the base 10, goes to approximately 14.3. It's actually very, very high. If you use the orthopoly approach, which is the work of Vivek's groups, Vivek Kadambe, that's about 6. And random Khatri Rao is at about 4.75. This is the work that's coming from Krishna's group. And our approach, when we embed rotation matrices, gives us about 2.6. Now, Krishna's approach is actually a random approach. So you have to choose a lot of random choices and then pick the best one. So here we pick the best after 200 independent random trials in our work. Okay, so here are, I mean, if I were to plot it as a, normalized MSE versus SNR. So what we did basically is computed this normalized Frobenius norm. So you are trying to recover A transpose B, so you're recovering something, you look at the Frobenius norm of the result and normalize it by the Frobenius norm of the original. And so here is what we get basically. So, I mean, as the results you would expect. So this is Fahim and Kadambe, this is Krishna's group. And basically the polynomial code is so high, I mean, so we don't even plot it because it's like completely unusable. So we see that we get very good results, and it's sitting right on top of what you would expect, which is the curve corresponding to the complex unit circle points. So any questions about this? Yes. 5. Oh, okay. All right. Is it 5 minutes or 5 minutes plus? Okay. So recommended, not required. Okay. So I think I'm learning from Mitan. So so let me talk about now the second part, which is about partial stragglers and sparse input matrices. So here are some of the results we have, and since I'm a little short on time, I'll try to go a little faster now. So here is one basic question we asked. He says, okay, so we are going to split our matrices into 3 parts, but let's suppose that I'm not willing to do actually any coding. As we discussed, when your matrices are sparse, you have to be careful about whether you should code or not. So if you did not do any coding and you simply tried to place these uncoded parts, but now every worker has a particular sequence. It's going to take the top, then the next, so going from a top to bottom order. This is this so-called cyclic assignment, where this one gets A0, A1, A2, and then A1, A2, A3, so on and so forth. It turns out that we can actually precisely bound what the queue for this scheme is, or precisely calculate what the queue for this scheme is. And the idea is basically, if you let, for example, the scheme go in such a way. So when you're talking about partial stragglers, different workers could be operating at different speeds. And modeling that is actually quite difficult. So the only question we are asking is, in the absolute worst case, over all possible speed patterns of the workers, how many submatrix products do you need to calculate? So here you see that A4 transpose X is going to be missed by across the entire cluster. So for example, here in the worst case, the moment you can calculate any 10 submatrix vector products, you will get your answer. Okay. And this, in fact, interestingly enough, matches a corresponding lower bound on Q. So if you're not doing any coding, we can show that this is the best you can do. But then we can do, of course, something quite a bit better with coding. So we have a scheme that has, let me just say what it does. It has the optimal straggler resilience. It has a low Q over delta value. So again, Q is the worst case number of calculations you need to do before you can recover your result. And it's also suitable for sparse input matrices. So the idea is exactly what Rudiger was also talking about earlier. So we are going to subpacketize a little more finely. So we are going to partition A into not just Ka submatrices, but we are going to partition it into the LCM of the number of workers and Ka. But B, we are going to only partition into Kb. And we also divide these matrices into certain number of classes, and we only code within a class. And some more ideas, we use this idea of so-called block cyclic assignment, and then most of the assignments are uncoded. So let me demonstrate by an example. So you have a scenario with 5 workers with A and B being stored half each, and we have 5 different classes. So, and the way you set up these worker assignments is, you go from top to bottom, C0 through C4, but then you do a block shift. So you move out C0 and C1, and then you keep going in that block cyclic fashion. And you take a random linear combination of the B submatrices. And this particular layer is the only one that is going to be coded in every worker. Okay, so the coding only happens towards the very end of the computation. All right. And so if you see, there are some nice properties that this has. So if a particular class is going to appear in every single worker, and a particular class also appears in every single location. So this appears at the top, second, third, fourth, fifth. So that allows us to bound the Q value of this worker. In particular, in this case, we can show that this scheme is resilient to any full one straggler, so one failure, and it has a Q of 23. So you would want to, at the bare minimum, calculate 20 such submatrix products, submatrix products, but you can, in the worst case, you have to calculate 23. So we can actually do this calculation for this case. So this is one of the theorems that we have, and I don't think I have time to go into the results. So the main point I want to say is that we do not lose anything with respect to, let's say, the original polynomial scheme. Our threshold is exactly the same when we talk about how many stragglers we are resilient to. And we also have a somewhat ugly looking expression for the worst case Q value here. But let me parse this a little bit here. So this is somewhat ugly because of the way the numbers are, and we have to take certain least common multiples and so on. But if n and ka are co-prime, which is to say that LCM is simply the product, and let's suppose that the number of stragglers is much smaller than the number of workers, which is the practical case, then we can show that Q by delta is approximately 1 plus S divided by N. So the overhead with respect to how much more you need to compute is this fraction S divided by N. Okay, so that is that. So let me skip this here. Okay, so let me talk about sparsity now. So if you look at this particular scheme, 4 of the assigned A submatrices here are basically not coded. You're just getting something because of the cyclic nature of our shift. Only the bottom layer is going to be coded. So most of the time when your cluster is operating, let's say, well, you don't even necessarily need to do any coding of A. I mean, you do have coding of B, of course, but all right. And this does reduce the worker computation time. So again, we can show that the storage fraction of coded A submatrices is again this 1 over Ka S by N, which is much smaller. And let me show you some numerical results here. So, okay, so here is, I think, something which is nice. I'll wind up soon. So 24 workers, and this is an extreme case. Both the matrices are 98% sparse. Only 2% of the entries are non-zero, chosen randomly. And so we assume that the slower workers have 1/5 the speed of other workers. Okay, so this is the scheme that, I mean, it's not written here, but the scheme has a threshold of 20. So if you see here, as long as the number of workers is at most 4, roughly all schemes are doing quite well. This is our scheme, the class-based approach. This is RKRP, which is the Krishna's group, and this is the polynomial code. In terms of the overall computation time, and I'm not plotting numerical stability here, but in terms of overall computation time, there is some difference, but not much. But the moment you have a 5th worker node that is also very slow, for these schemes, orthopoly and polynomial, they really jump up. Okay, whereas in our case, because we have this low Q value with respect to delta, it doesn't jump up so much. It goes up, but not much. Okay, so here are some more results. We can actually characterize this so-called how bad this Q by delta is for our constructions. And so that's about it. So I mean, to conclude, so I think there are several relevant issues within coded computation, some of which I highlighted in this talk. And one interesting thing is that, so this is an workshop on application-driven coding theory. So if we want to apply them to a different domain such as coded computation, we need to be aware of the system constraints. So this numerical stability is not a non-issue there; it is a big issue, so which needs to be taken into account. And this issue of partial stragglers that I also talked about. So I mean, some open questions, like I said, numerical stability. And I think there are a lot of open problems. So whatever our scheme that I discussed is numerically stable in the regime when the number of stragglers is small. If the number of stragglers blows up, then we still don't have any way of controlling the worst case condition number, even in our scenario. And again, the case of sparse matrices and matrices that have certain sparsity structure, I think that could be a very useful thing. And understanding this Q by delta metric a little bit better and corresponding better code constructions.
Thank you. We have time for a question or two.
Yes.
So, if you look at the origin, the Strassman's algorithm, it automatically already did the thing when you do 2 by 2 that it gets away with 7.
7, yes.
So, is there any way to build it on top of that?
So, I mean, the individual workers could themselves be running Strassen, and that would speed things up for them. That's like a vanilla.
Because it's naturally already split into
right. So the workers, the matrices that they are given, they are completely oblivious to whether they've been encoded or not. So workers could take that, block it, and run Strassen on it.
So that would take the original Strassen thing and assign that to the workers, right? But I don't know how you will still need coding on top of it. It's also numerically not.
Yeah. So I believe there was some work in this topic.
Shinpo has done this.
yeah, that's what I was saying. Ivan Dursma, right?
Placement with Strassen.
Yes.
Ask him afterwards. I can't say exactly what it achieves.
Dursma's group, right?
It's been done.
Okay, yeah. Yes. I mean,
splitting computation in two does not mean that time splitting splits in two because these are random variables. So you can have 3 different models, for example, that Phil and I consider. How the random variables scale, right? It could be additive model, one is independent of the other. It could be something called observer model. If the first block is slow, the second block will also be slow, etc. So just splitting computation does not mean that the time scales in half.
I mean, for a given worker, I mean, you're saying like it.
Depends on the system. Like if it's some high performance computing where you pay for something to be done, then yes, you can probably count on that. But if it's some kind of work on cloud where you are computing with other jobs, these servers are also computing not only your job
but other jobs. I see.
The variables and the struggling comes from
that variation, I see.
From the potential computers, not because I mean, if you have particular computation, it's not struggling.
Right. Okay. Yeah. That's definitely a reasonable point. So none of this analysis here takes any kind of randomness into account of the worker nodes. I mean, the assumption is that yes, if you're scheduling less, you will take less amount of time. But yes, there is randomness in that as well. Yes.
I have a comment and a question. So typically, they also look at another metric, which is the amount of data that you have to send over. The communication cost in addition to the computation cost.
Yes.
So if you take your real numbers and put them into complex numbers, you typically have to end up sending twice the number of computation, even if you, by whatever model of computation cost, whether it's the same or not. Second thing is that even though the Solomon code based constructions are bad from a numerical point of view, there is something very nice about them.
Yeah.
Is that the reconstruction cost is only quadratic because the Vandermonde matrix can be inverted cleverly. Right? At least like the random constructions we lose that.
Mm-hmm.
How
So,
about your constructions? Are there today?
So yeah, so that is a good point. So to answer your first question, so like I said, we actually do not do any complex computation or any complex transmission also. Everything is purely real. And we do not take any additional hit in communication cost. So that is not an issue. The second issue, yes, the system of equations that we get does not have that nice structure. So, okay, so we can do some things, and we've tried both approaches. It doesn't necessarily help us. I mean, yeah, okay, overall decoding time here is going to be higher. But yes, so that is true. So you lose the very nice structure of the equations that you have. Yes, Rashmi.
I'm curious to know if the approach can take any dependency in the inputs into account. So to elaborate on that, along with my business student Michael, so we've seen how the it's a lot estimators that kind of their groups work on polynomial tools, right? It's like Lagrange, what they call it, Lagrange for computing, can be viewed as local decoding on a read model. So basically, it's a polynomial function, and then you're evaluating at different points. And you can look at it as a read code and as a local decode.
I see.
Okay, so and when you take that viewpoint, so we called it locality-based view. It's the same scheme, but it's a completely different viewpoint. It's a different perspective. So when we take that viewpoint, what is possible is now instead of just taking the dependency that is introduced by the code, any other kind of dependency, for example, like might be there in the original data inputs,
I see.
can be exploited. Like for example, as Aditya was mentioning, if you break up the big matrix into smaller matrices and use the straggles algorithm or any other kind of algorithm, there is dependency in these sub-computations that are done. They are not completely independent sub-matrix implementations. Because you are splitting into some sub-matrices for A, sub-matrices for E, and then you do computations. So there are dependencies among these sub-computations. And that dependency can be exploited to reduce the workload. And many other tasks, like for example in machine learning, also there are these dependencies. I'm happy to chat.
Yeah. So I mean, I think this is a.
If such dependencies can be exploited here too.
So I think for sure that if you consider, for example, the class of sparse matrices, where there is, like I said, there's some kind of block sparsity structure, I think things can be done there. That could be quite valuable actually in certain scenarios.
Yeah.
Let's go.
All right, maybe let's finish up and take the.
Actually, I wanted to say one thing. I know Krishna has been giving people a hard time about repetition code. So I wanted to say something before we conclude, if I may. So in a different alphabet, Toda, Shishe, Danke. That's all the other languages I know. Thank you.
That's nice. I mean, that's what I was expecting, but people decided to drop the thanks as a way of not doing the repetition.